In this lesson, we'll configure analysis settings in ideCAD, country and codes, ASCE 7 seismic with AISC 360 steel, and diaphragm and eccentricity options. You'll learn how to use the Seismic Wizard to pull USGS spectra, set SMF, SCBF with R, omega, and CD, and fine-tune drift, period, and redundancy factors. We'll also cover spectra, thermal, wind, and bolt, weld methods. By the end, your project will be analysis ready and code compliant. We'll continue with the analysis settings. You can access them from the ideCAD icon at the top left corner of the screen. Hovering over it highlights the area in a different color. Click it once. In the window that appears, navigate to the General tab under Analysis Settings. If you recall, when we first created the project, we defined the building codes and performed some initial adjustments before starting the modeling process. You can always return to this section to revise any settings after completing the project modeling. We reach this area via Analysis Settings, General, Project and Building Code options. Clicking once opens a window where the software asks for country and code selections. We previously selected the United States. The initial setup covered these options, so I will not detail them again here. You can select from the available country presets as needed. I'm continuing with the United States, using metric kilonewton units. I click Next. On the Building Codes page, we selected ASCE 7 for seismic design and AISC 360 LRFD for steel elements and connections. Although the project does not contain reinforced concrete members, we'll be modeling RC foundations later. The ACI 318 code is active for concrete members. Load combinations and wind load standards are also selected. The software automatically calculates all relevant parameters based on these selections. I click Next. For steel, we chose European standards for bolts, fasteners, and steel profiles. Clicking Finish completes this phase. Now, let's take a look at the remaining options in the General tab. First, you'll see the seismic force calculation method. Note that some methods appear grayed out. This is because ideCAD Structural applies modal response spectrum analysis for new building designs, using the modal combination method by default. As a side note, the software also automatically performs irregularity checks. These checks are conducted using forces calculated by the equivalent lateral force method, but all member designs and element checks are based on modal combination results. I'll explain these in detail in the reports section later. Under diaphragm eccentricity effects, you'll find two methods for accidental eccentricity: dynamic eccentricity and static eccentricity. If you select the dynamic method, the software will perform 4 separate modal analyses. This method is beneficial for tall buildings, irregular structures, and amorphous architectural forms, as it yields more accurate results. When selected, the software displaces the mass center of the rigid diaphragm by 5% in both the X and Y directions, positive and negative. This creates 4 distinct modal analysis models, each representing a different torsional load case. The resulting 4 cases are then combined using the SRSS or CQC methods, and the combined results are displayed as X and EY load cases. As I mentioned, this method provides a more realistic analysis for irregular or high-rise buildings. The downside is a slightly longer analysis time. The static eccentricity method, on the other hand, is a conventional method where the mass center is displaced by 5% on the rigid diaphragm, and torsional effects are included in lateral force calculations. This artificial offset generates torsional moments, which are distributed to the structure as additional lateral loads proportional to the eccentricity. This method requires the system to be regular and low-rise. Its advantage is faster analysis and ease of manual verification. Now, moving to the diaphragm modeling method, we have two options: rigid diaphragm and semi-rigid diaphragm. The sub-options here are mostly related to reinforced concrete design options, so I won't dive into those. As mentioned in the steel slab modeling section, the software automatically distinguishes between diaphragm types. Composite slabs, trapezoidal or solid, are modeled as rigid diaphragms, while metal slabs are considered flexible diaphragms or are analyzed without a diaphragm assumption, as they don't contribute to in-plane stiffness. Now, let's look at seismic code parameters specific to American codes. ideCAD offers a Seismic Design Wizard for quick and accurate setup. When you click it, the wizard window opens. The wizard helps prevent errors by guiding you through code limitations related to soil class, building height category, basement levels, and seismic design category. Note that this wizard is only available for USA and Turkey selections. For other countries, manual adjustments are needed. For instance, if certain structural system types or ductility levels are not allowed based on your selections, the software will automatically disable those options. Let's proceed with an example. We start with the soil type selection, referencing ASCE 7 tables. I selected soil type C and clicked OK. Then we move to risk category, with choices from I to 4, which correspond to seismic importance factors of 1, 1.25, and 1.5. I will choose risk category I with an importance factor of 1 for this example. On the next screen, we configure parameters for the horizontal response spectrum. You can select a point directly on the US seismic map. The software will fetch the corresponding spectral acceleration values, SS, S1, from the USGS seismic hazard tool. Note that this feature works only within the US borders. After selecting a location, the latitude and longitude are displayed, and the online button retrieves the site-specific seismic parameters. The software automatically calculates the horizontal elastic response spectrum using these values. You can override the TL, long period transition period, if needed. Moving forward, the vertical spectrum parameters are displayed. These values are locked to prevent accidental errors. You can see the vertical response spectrum curve in the preview below. Next, the software determines the seismic design category, SDC, based on the SDS and SD1 values and building risk category, referencing tables 11.6 to 1 and 11.6 to 2 of ASCE 7. The system automatically selects the appropriate SDC and explains the reasoning above. For example, if values under risk category 4 are invalid, those selections will be disabled to prevent mistakes. Moving to the Stories tab, we see parameters like Live Load Participation Factor, LLF, which is set to 0.3 by default. You can adjust this value as needed. There's also a rigid story checkbox. Since this project does not include a basement level, there's no need to mark any story as a rigid basement. However, if a basement exists and qualifies as a rigid floor according to the code, it must be flagged accordingly. The software will consider this selection when determining the building height, HN. Additionally, if the top floor's footprint is significantly smaller than the floors below, such as stairwells, elevator shafts, or mechanical rooms, these levels should also be excluded from the building height calculation by marking them appropriately. In this project, there's no basement, nor any stairwell or mechanical room at the uppermost level, so I will proceed without making any selections. I confirm with OK and continue. In the next tab, we need to select the building type. Among the options, reinforced concrete, steel, and RC and steel, I chose steel. The following tab is for the diaphragm type. Since this project uses composite slabs, I selected rigid diaphragm. For the lateral system in the X direction, I designed a moment-resisting frame, so I selected system type C. But let's step back for a moment to see this. Due to certain conditions of the building, not all system types are selectable. The grayed out options are disabled, which helps guide you in making correct selections and prevents potential design mistakes. I will now select C1, which corresponds to the special moment frame. As you can see, parameters such as the R factor, overstrength factor, and deflection amplification factor CD are all displayed. Additionally, based on the building height, you can verify whether there are any restrictions for this system type. After confirming C1 for the X direction, I proceeded to select B2 for the Y direction, which is the special concentrically braced frame. I then saved these parameters. Once saved, the selections automatically update the corresponding settings in the ASCE 7 configuration panel. For example, the ductility level in the Y direction is now set as a special concentrically braced frame, while in the X direction, it is assigned as a special moment frame. Accordingly, the system behavior coefficients, R, overstrength factor omega, deflection amplification factor CD, and the redundancy factor, are all updated and active in both directions. The redundancy factor is set to 1.0 by default. The software does not automatically verify whether this coefficient needs to be modified. According to the American Code, this factor should be either 1.0 or 1.3, and it is up to the user to determine the correct value and manually enter it into the respective fields for both X and Y directions. Additionally, for irregularity checks performed using the equivalent lateral force procedure, the relevant coefficients required for period control must also be specified here. This allows you to directly adjust the CT and X parameters used in seismic period calculations. The accidental eccentricity ratio is set to 5% as per the code, but if a different value is needed for specific cases, you can modify it through this field as well. You can also change the building risk category here. If you wish to apply a custom definition for vertical seismic effects, you must activate this checkbox and input the desired value. Typically, the software applies vertical seismic loads to structural elements in compliance with ASCE 7, and these can be monitored within the load combinations and load cases. For this project, I'll proceed with the default settings in accordance with the code. Below, you can see the structure type options: reinforced concrete, steel, and RC and steel. I'll continue with steel, as we've already configured this through the wizard. The software also performs drift checks automatically. However, you have the option to adjust the allowable drift limit from this section. Switching to the Response Spectrum tab, you can see both vertical and horizontal elastic response spectrum curves. The red curve represents the horizontal spectrum, while the green curve shows the vertical spectrum. Based on the site class, you can modify the parameters here to generate the spectrum manually, without using the wizard if needed. The staged construction analysis is currently not available for steel structures, so I will skip this part. In the thermal loading section, you can perform analysis based on two different temperature differential values applied to the entire structure. For thermal loads, you can define two temperature difference values for the whole structure or assign T1 and T2 for each story individually. The method of calculation, whether based on modulus of elasticity or moment of inertia, can be selected here. In the wind loads section, TS498, Turkish code, is inactive. Eurocode is active, offering 4 different calculation methods: open structures like scaffolding and transmission towers, tall buildings, H/D greater than 5, rectangular buildings with a monopitch roof, and double pitch roofs. We're selecting the double pitch roof method for this project. Below, you can adjust various coefficients per code. As mentioned, you can also manually input wind pressures on sheeting elements if needed. At the bottom of the tab, you can activate input fields to manually apply additional wind loads to diaphragms by checking the Apply Extra Lateral Wind Loads to Diaphragms box. This enables you to enter custom wind forces in X and Y directions for each story, which are combined with the auto-generated wind loads to account for cases such as facade-mounted equipment or localized wind effects. Switching to foundation settings, you'll see dry soil unit weight, saturated soil unit weight, soil type, cohesive or non-cohesive, etc. I'll skip the detailed parameters as these are covered in the reinforced concrete design trainings. Moving to steel design options, you can choose between two methods for bolt group and weld analysis, the elastic method and the instantaneous center of rotation method. Let's briefly discuss these. The elastic method assumes all bolts and welds share uniform stiffness, with forces distributed proportionally based on their distance from the load axis. This approach is simple and effective for regular, symmetric connections but fails to capture stiffness variations or realistic torsional effects in irregular layouts. In contrast, the instantaneous center of rotation method, ICR, determines a real-time rotation center under loading, distributing forces based on each element's distance from this point. It accounts for both axial and rotational effects, providing a far more accurate load distribution in asymmetric or complex connections. In practice, the elastic method is ideal for quick checks and symmetric layouts, while the ICR method is essential when torsional behavior and connection irregularities demand precision. Below, you'll see strengthening options, but note that the software does not currently support performance-based seismic assessment or retrofit design for steel structures. These options pertain to reinforced concrete. Lastly, in the Other tab, you can define the environmental exposure class. When you click the drop-down toolbar, a list will appear where you can select the appropriate class. You can also make this selection here to ensure that this node appears on the drawing sheets. Now I'm going back and clicking the OK button to proceed. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.